Hello viewers, in this part of the program, I am going to discuss the elementary idea of drainage on farms. Drainage and irrigation both are important aspects of water management. In irrigation management, the optimum quantity of water is to be supplied to the crop for the full period of the crop growth. Whereas in case of drainage, the excess amount of water available on the surface and in the root zone depth is to be removed in a short period of time. From the production point of view, both irrigation and drainage are important. Drainage is the artificial removal of water in excess of the quantity required for the crop. Drainage includes removal of excess surface and subsurface water in the root zone. Irrigation system aims at supplying optimum quantities of water throughout the crop period. Drainage system aims at removing excess quantity of water in a short time. Often, both may be required together to assure sustained and high level production of crops. Drainage of excess water from irrigated fields is necessary for satisfactory growth and yield of crops. Causes of waterlogging. Waterlogging is caused when inflow into groundwater exceeds outflow from it. The problem is serious when hydraulic conductivity of the soil is less than 2.5 cm per hour. Water logging is generally due to heavy rainfall and over irrigation, seepage from the reservoir and canals, floods in rivers spread to cultivated land, and low elevation of lands. Whenever there is continuous rainfall and heavy rainfall or over irrigation, or whenever in low lying land there is inflow of water from the surrounding areas. Generally, the inflow of water in the soil is more than its outflow, and under these conditions water accumulate on the surface of the soil as well as in the root zone depth. This water is responsible for waterlogging. Effects of waterlogging. Waterlogging is generally defined as the condition where water table is less than 3 meters from the surface. At this depth, water from the water table rises at significantly rapid rates by capillary action to the ground surface. Waterlogging reduces soil aeration. It results buildup of carbon dioxide, methane, ethane and propane in the soil. Uptake of nutrients is adversely affected. Salts are brought to the surface layer, results salinity. Root growth is restricted and yield is reduced. Due to the problem of waterlogging, exchange of gases from atmosphere to soil and from soil to atmosphere is restricted. As a result of restriction in exchange of gases, the concentration of oxygen in the root zone becomes less and the accumulation of toxic gases like carbon dioxide and methane becomes more in root zone depth. Under these situations, the root growth is restricted. Moreover, the uptake of nutrients is also less under these conditions. Benefits of drainage. Good drainage facilitates the ready diffusion of oxygen to the root zone and escape of carbon dioxide from the root zone. Drainage permits roots to grow deeper and spread wider, which extract more nutrients. The provision of a good drainage system permits the removal of excess salts. Drainage improves the activity of aerobic organisms. Drainage provides conditions favorable for high crop production. Due to drainage, congenial conditions prevail in the root zone, and a result of congenial conditions in the root zone, the microorganisms population increases in the root zone. Microorganisms in the root zone increase the availability of nutrients. When there will be more availability of nutrients, more oxygen, definitely there will be more uptake of nutrients, and the root growth will be more. Due to profuse root growth, the volume of the soil covered by the roots will be more. Drainage systems. There are two general types of land drainage systems: surface drainage and subsurface drainage. Surface drainage removes excess surface water from the fields. Subsurface drainage removes excess water from the crop root zone depth of the soil. Both the types of drainage are necessary, surface drainage and subsurface drainage, so that the excess water may be removed from the surface as well as root zone depth. Surface drainage. Removal of free water tending to accumulate over the soil surface is called surface drainage. It is generally carried out by shaping the land so as to direct and dispose of overland flow. There are 4 types of drainage systems used in flat areas having less than 2% slope, and one system for sloping areas where slope is exceeds 2%. Random system, parallel system, parallel open ditch system, bedding system. These 4 systems are used in comparatively flat areas, and the interception system is being used in sloping areas. Random system. It is used where small scattered depressions to be drained occur over the area. Drains are usually designed to connect one depression to another, and water is conveyed to an outlet. Open drains, besides occupying land area, are likely to interfere in farming operations. This figure shows the layout of random system. Here there are depressions and water accumulate in these depressions. Then these depressions are connected to each other and ultimately water is drained out. There are 2 disadvantages in this system, that more area is occupied by this system. Moreover, these interfere the farming operations. Parallel system. It is the most effective surface drainage system, well suited both for irrigated and rain-fed areas. Individual fields are properly graded for discharge into field drains. The field drain may discharge into field laterals bordering the fields, and the laterals in turn lead to the mains. Laterals and mains should be deeper than field ditches to provide free outfall. This is also referred to as field ditch system. In this system, as shown in the figure, the field is graded in such a way that the surface water comes towards the bordering area of the field, and these lateral drains collect the water, and this water is drained in main channel. Parallel open ditch system. It is applicable in soils that requires both surface and subsurface drainage. It is similar to parallel field drain system, except that the drains are replaced by open ditches which are relatively deeper with steeper side slopes than the field drains. This is also known as diversion ditch system. This system is almost same to the parallel system. The only difference is there, the lateral drains in parallel system is shallow, but here these are deeper, and the main drain is also deeper in this system. So both surface water is drained out, simultaneously partially subsurface water is also drained out. Bedding system. It is adopted when the slope of land does not exceed 0.5% and in slowly permeable soils. Parallel beds are developed by shaping and smoothing the land surface so that runoff drain laterally from the beds into dead furrows created in the same location each year by plowing. Dead furrows lead runoff into cross-slope collection and finally into an outlet ditch. This bedding system is being adopted in heavy textured soils where soil permeability is less. Beds are formed parallel, and in these beds water is drained off towards both sides in dead furrows, and from these dead furrows water is collected to the collection ditches, which ultimately comes to the outlet ditch, and ultimately water is drained out of the field. Interception system. It is adopted in sloping areas where slope exceeds 2%. It consists of a series of shallow open drains across the slope with a mild grade to intercept and remove surface runoff. It is also known as cross slope ditch system. This is the system. It is adopted in such a manner that there is minimum erosion of the soil with the runoff water. Subsurface drainage. Subsurface drainage refers to the natural outflow or to the artificial disposal of excess water within the soil or subsoil, and it generally involves lowering the water table or preventing its rise. It is also known as groundwater drainage. Soils with high water table in the profile needs subsurface drainage. When the water table becomes higher, under that condition the water reaches to the surface of the soil by capillary action, and in these situations there is necessary to lower the water table, and subsurface drainage is necessary to lower down the water table. While surface drainage removes excess rainwater in the root zone before it affects the crop, subsurface lowers the water table to provide better environment in the root zone. In subsurface drainage, water moves to outlets under the influence of gravity. Pipe or tile drains, mold drains, deep open drains, and combination of tile and open drains are commonly used in subsurface drainage. So, mainly in subsurface drainage, tiles or pipes and molds are being used. Sometimes open drains are being used, but since the open drains affect the operations in the field, so mostly pipe drains or mold drains are being used in subsurface drainage. Pipe or tile drainage. Continuous line of pipes or tiles laid at specified spacing, depth and grade remove excess water from the soil profile. Perforated PVC pipes have replaced the tiles. Tiles or pipes of 360 to 600 centimeter length having 10 to 30 centimeter diameter are used. Grades vary from 0.15% for 10 centimeter diameter pipe to 0.05% for 30 centimeter diameter pipe. The flow velocity of 30 to 45 centimeter per second is maintained to carry the sediment getting into the pipelines. Pipes or tiles should be placed at 60 to 70 centimeter below the soil surface. The lateral distance of the pipes and the depth of the pipes depend on the site characteristics and rainfall behavior of that particular region. Mold drainage. Mold drains are cylindrical channels formed at a desired depth in the soil profile. There is no lining material, and the inherent stability of soil gives stability to the mold drains. Water entering throughout the mold drains is guided to the outlet. These mold drains are connected to each other and water is drained from the field. Layout of pipes or drains. Layout of pipes or drains can be of several ways. Random or natural system is used for draining isolated patches and when entire area does not need drainage. The herringbone system is used in areas where a main line or sub-main could be laid in low area and laterals could be drawn from both sides. The gridiron system is similar to herringbone system except that the laterals enter the main only from one side. It uses less number of junctions and hence economical than herringbone system. Layouts such as double main, diagonal, interceptor, mixed, etc. are followed depending on topography of land to be drained. So, the different systems and layouts are being adopted depending on the topography of the land. These layouts and arrangements have been shown in this figure. In A, the parallel single mains are laid out. In B, parallel with double mains. C, gridiron. D, mixed system. E, herringbone. F, intercepting system has been shown. The cost involved in C, that is gridiron, is less in comparison to E, that is herringbone. In case of gridiron, laterals come only from one side and the junction points are less, whereas in case of herringbone system, laterals are coming from both sides and junctions are more. So, more cost is involved in herringbone system in comparison to gridiron system. Drainage coefficient. It is defined as the depth of water in centimeter to be drained in 24 hours period from the entire drainage area. Drainage of 1 hectare centimeter in 24 hours equals drainage of 1.157 liters per second. It is also expressed as the flow rate per unit area. The coefficient helps to determine size of the drain. Drainage coefficient is decided such that no appreciable damage is caused to the crops grown in the area. For open ditches in small areas, the value ranges from 0.6 to 2.5 centimeter. Intensity of rain and its duration are inversely proportional to the time allowed for removal of water. A time interval of 40 hours for removal of storm runoff for field crops and 72 hours for wet season rice are adopted. Drainage coefficient is very important and for layout of the drainage system, drainage coefficient is necessary to determine. Only after determination of drainage coefficient, the layout of the drains is decided. Factors affecting flow rate from soil to drains. Hydraulic conductivity of the soil, water table, that is constant depth or falling water table, depth of the drain, horizontal spacing between drains, character, open ditches or tubes of the drains, nature of the gravel used, diameter and slope of the drains, rate of seepage or recharge to the groundwater. So, these are the factors which are important and these factors affect the flow rate. I am quoting one example to calculate the capacity required at the outlet end of the discharges draining a watershed of 500 hectare with a drainage coefficient of 5 millimeter. In this case, the total quantity of water to be drained in 24 hours has to be calculated in cubic meters and it will be 5 into 500 into 10,000 divided by 1000. It is 25,000 cubic meters. Then this discharge is in 24 hours. So, per second discharge has to be calculated. 25,000 will be divided by 60 into 60 into 24 and the value is 0.289 cubic meter per second. In this part of the program, Elementary ideas of drainage on farms have been discussed. Drainage is very important for higher crop production. When there is poor drainage, then water accumulate on the surface of the soil and in the root zone depth, and as a result of water accumulation, yields are adversely affected. Therefore, drainage is necessary. Both surface drainage and subsurface drainage are necessary. From surface drainage, water is removed on the surface, and in subsurface drainage, water is removed from the root zone depth. Different patterns of the drainage depends upon the site characteristics. Hope you have enjoyed the program.